Great. Okay. Then let's talk about the extrasolar planets. So last time we talked about the different methods of finding extrasolar planets, and we found that there were probably like 5-ish good methods to find extrasolar planets, of which really 3 are something that we can be active about. We can use the radial velocity method. That's a big one. This one looks at the shift in the spectra of the light, because the gravity of the planet tugs on the star towards and away from Earth. And this red shifts and blue shifts the light from that star, this wobble that the planet causes. And so measuring that wobble and the wavelength of the light produced by the star at its spectra, that tells us that there's a planet there. And from this method, this radial velocity method, we can determine the planet's minimum mass. We know it's at least such and such size and mass. We know its orbital period, so we know how long it takes to orbit its star. Because we know its orbital period, we also know its semi-major axis, so we know how far away it is from its star as well. And we get its orbital eccentricity, so we know how elliptical its orbit is. We know if it's very, very circular or if it's very, very elliptical, essentially. And this was the primary method to find extrasolar planets until Kepler arrived, with a huge upgrade in technology, essentially. Kepler's method was to look for what are called transits. Transits are when the planet passes in front of the star relative to Earth, and it blocks out a very, very, very small percentage of light. Kepler measures a 0.008% difference change in light. So the amount is very, very, very small that the planet blocks out. But if you look at, 300,000 stars, then the alignment of the star and planets does work out in enough cases for you to find a good percentage of stars. Now, not all stars have planets that pass directly in line with our plane relative to the star. And so if that happens, then we just can't detect those. That's not to say that they aren't there. Based on the amount that we are seeing, it matches what would suggest that all stars basically have planets, but it's just that most of those planets can't be detected with our current techniques. But the statistics would suggest that, if we are finding how many are having planets at the level that we're finding that are having planets, it would suggest that most have planets, actually. Anyways, with this transit method, you can determine the radius of the planet, so how wide the planet is. You can determine the orbital period, so how long it takes to orbit. Based on how long it takes to orbit, you also get its semi-major axis. And as of today, the transit method is the most successful method we have at finding extrasolar planets. But you can direct image planets. This has been done. There's just a handful of planets that have been detected in this way. HR 8799, I believe, is the picture shown here, which has 4 orbiting planets. These are like Jupiter-sized planets at about 10 to 100 AU away from its central star. This technique will probably keep increasing and increasing and increasing as technology gets better and better and better. For now, this is still pretty tricky. The planets have to be huge in order to be detected, just because they need to reflect so much light for these instruments to detect them. But I expect this will get better and better and better. Gravitational lensing is kind of this, the stars literally aligns kind of luck-based technique. And so I guess just because it is lucky, it will continue to happen. And they can kind of go back in the records of looking at light for stars and seeing that it kind of gets magnified due to this lensing effect every once in a while. Or at one time, because I doubt it happens multiple times. But at least for the same planet. But yeah, so there's this lensing method. It's a luck-based method. I don't expect this one to kind of be focused on, and kind of when we find it, great, but it's not going to be a huge effort. And then astrometry might increase as we get better and better kind of precision of measuring stars' locations. But this one's tough because like the sun is moving through space, all the stars around us are moving through space. Having like the exact location of all of these moving objects where we ourselves are those moving objects as well, it's a pretty tricky question. And so having like defining precise locations and then measuring everything very, very accurately based on those definitions is kind of what's important here. I know there's a couple spacecraft working on trying out finding planets and using this method kind of in the works. All right, so we've got these different methods of finding planets, radial velocity and transits being the primary successful methods so far in human history. Based on what we found from them, giant planets are preferentially found around stars that are abundant in iron. So high metal stars have more giant planets. What this tells us, this kind of makes sense because the giant planets, to have a giant planet, it needs a big core really, really early on in the formation of the stellar system. And so if you're going to have that really, really big core, you need more metals because the metals are denser. So that kind of goes together, and I think that would support that same idea for solar system formation, that the giant planets are more likely around those that have more metal. All right, what else can we measure? How does it compare to our solar system? And then what do we learn based on what we know about the extrasolar planets? So first, here is a graph of the eccentricity. So that's how elliptical the orbits are compared to the orbital distance of the object for a good number of the known planets plus our own solar system. It should look like kind of a lot of other planets are even more highly elliptical. There are some that are much, much more elliptical, some approaching 0.9. So that's extremely elliptical. In our solar system, the most elliptical would be Mercury at about 0.2. But then there are huge clusters at 0. So some are very, 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 very circular as well. Kind of huge stack, very, very close to 0. Our own solar system is kind of at around 0.1 to 0. What else? It looks like also the bigger planets kind of tend to have a wider range, and the kind of further you are as well, the wider range of eccentricities. When you're very, very close to the star, if you're orbiting very, very close, you're more likely to have a circular orbit. And when you're kind of further away from the star, you have a wider range of possibilities. You could be very circular, or you could be very elliptical, especially that high eccentricity, that highly elliptical is possible only when you're further away from the star. Here we have another graph. This one is showing the mass of the planet in regards to how far the planet is from the star. And it's color-coded as well by the method the planet was found. So red is the transit method, blue is the radial velocity method. You'll see a few brown dots in there, which are the direct detections, and then a few green dots as well for some gravitational lensing. And each dot is a different planet that's been detected, that's known about. So the mass on the left axis, or on the y-axis, kind of is in Jupiter masses. So all of the Earth-like planets are kind of at 0.01 level here or below. So that would be like the Earth mass, roughly. And then the Jupiter planets are kind of at that 1 on this kind of a level here. And we are measuring the distance of those planets from about 0.01, so that's like 5 times closer than Mercury, to about 10, which is kind of where Saturn roughly is today. So that's kind of the range that we're able to look at. Kind of you'll notice there's kind of a gap in the 0.01 mass planets, kind of further away. So those low mass ones that are far away from their stars have very, very little effect on their stars. And so it's very, very difficult to detect them. So that's kind of why there's a gap kind of in that smaller size at further distance. Those are just too small to see with our technology. One interesting finding from this was the population of planets that have now been called hot Jupiters. So this graph kind of breaks the planets into these kind of different zones. You'll see kind of different clusters in these different areas. Kind of in the bottom middle is one cluster, and the kind of top left is one cluster, and then kind of in the top right there's another main cluster. And these main clusters kind of represent these different populations of planets. Kind of based on our solar system, you would expect the kind of bottom cluster and the top right cluster. So we have in the bottom cluster those Earth-like planets, those Neptune-like planets, those Uranus-like planets. And then in that top right cluster, those are all the Jupiter-like planets, or like super Jupiter planets, you might think. Right? Those would kind of seem sort of normal based on our planets. But then there's also those Jupiter planets that are super close to their stars. They're hot Jupiters. And so this is a population of planets that just doesn't make any correlation to our solar system. So we were kind of surprised when this kind of distribution first started showing so many of these Jupiter planets clustered in this kind of upper left location on this graph. Because it's not represented in our solar system at all. So this is a new realization we're going to have to come to terms with later. We have these hot Jupiters. What does that tell us about the kind of distribution or the evolution of solar systems with these Jupiter-like planets? Like how did solar systems with hot Jupiters form? What might that be like? So we have to think of maybe a new method of solar system formation to take these types of planets into account. Here is another kind of take on the eccentricity versus semi-major axis graph. So again, how elliptical the orbit is for the planet based on how far away it is. And then the color here is showing the mass of the planet. But in this case, it's based on Jupiter masses again, so not based on Earth masses. So the orange, yellow, red, green, these are the 10 Jupiter mass planets. And then kind of like the blues and blacks, those are the Earth mass planets. And kind of what I'm hoping you see is, again, kind of that same trend from before, that the very low semi-major axis, so very, very close in planets, are very, very circular orbits. Their orbits range from like 0 to 0.4 when you're very, very close. And as you get further away, that's when you kind of get the bigger ranges in eccentricity, in how elliptical your orbit is. And then also that the bigger planets, so kind of the bigger color variation, is also represented best in that further out zone at around 1 to 10 AU as well. So you don't have the bigger planets closer in as often on this graph. So their eccentricities, if they do exist, are very, 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 very small. So what properties of these detectable planets can we measure? So far we've talked about a couple. We talked about their orbital period based on their semi-major axis or their separation, which is their distance from each other. We can talk about the orbital shape, right? We can get at the eccentricity, how elliptical it is. We can find the planet mass, and we can find the planet radius. And if we can find both of those two, we can get the density, and the density is super important. We'll talk about why in a bit. In some cases, we can get planetary temperature. We can make models for planetary temperature in a lot of different ways, but we can actually measure it in a couple cases. And then we can also find the actual atmospheric composition of certain planets around other stars. That one's pretty crazy to me. And is maybe one of the most likely tools in finding kind of astrobiology in kind of like the wider solar system and the galaxy and beyond. Measuring this atmospheric composition is especially interesting. We'll get back to that. Any questions before I kind of go into some more of these measurable properties and what they mean? Okay. What can Doppler shifts tell us? So kind of I briefly mentioned this last time about the radial velocity method and how it detects planets. It's based on the shift in their spectra, red words and blue words in the spectra as the planet's gravity pulls and pushes the planet as it orbits. And so that spectra is this shift in the spectra is what's plotted in these graphs. And based on the shape of the graph you get from this, it tells you a lot about that planet. So the primary two things it tells you is the mass of the planet and the kind of the period of the planet. But then it also tells you how circular or how eccentric the orbit is as well. So the mass from the planet you get based on the strength of the shift. So when you have bigger and bigger planets, you get much larger gravitational shifts due to the size of that planet, and that would indicate kind of a higher amplitude in the wave you see in your radial velocity curve. Kind of like comparing the upper left image here to the upper right image here. You also get an idea about how circular or eccentric the orbit is. So a very regular circular orbit would have something like the bottom left graph versus something very eccentric, very oval shaped, be more like the bottom right graph. You also get a different idea about the distance, the average distance that the planet orbits at, based on these graphs, and that the period that the planet has depends on the distance the planet orbits at. There's a Kepler's law relationship that tells us this. And so you could have very, very, very close planets, which would be kind of like the period of the waves represented in the bottom left, or kind of further away planets, kind of like that bigger planet in the upper right here. So you get the orbital distance, or the orbital period, you get the distance the planet is, the mass, and how eccentric the orbit is, all based on these curves. And there's fancy math for that, which of course I don't expect you to know. But if you get a PhD in this, then you would. You can also get, in some cases, as far as the mass goes, actually in all cases as far as the mass goes, what we're measuring is actually the minimum mass, because since we're not directly detecting the planet, we're just detecting the gravitational shift that the star is experiencing relative to us. If it's not actually directly in the plane with us, the planet's mass has to actually be more than what we are calculating. So we know that the planet is there. We know it's at least so big, if not even much, much, much bigger. Because if it's not directly in line with us, if it's actually out of line with us, to have the same effect, it would need to be a much, much bigger planet. Because it would be further than we had actually anticipated based on our calculations. So what we're getting is this minimum value here. The planets could actually be significantly bigger if we're using this radial velocity method to detect them. In which case, since this is our method for detecting mass, they could actually be denser than we are anticipating as well. Here we are seeing transits for Kepler-11. Kepler-11 has, I think it was 6 planets that are all transiting at the same time. Well, maybe not all transiting at the same time, but sometimes the transits do line up, in which case the light curve from these objects get added to each other. So they're all blocking out light simultaneously, but sometimes they can pass in front of each other as well, so they won't be blocking out additional light because they're just blocking out the same light that the other one would have been blocking out anyways. So these light curves get very, very crazy. But if you assume these planets individually and just look for their own periodic signals, and then see what those are like when they stack up and how that matches, it does end up working out very, very well. So here, the planets, each one have their own different shapes, their own kind of length of transits. We get their periods all individually, ranging from 10 to 118 days in this case. Notice some of those periods are pretty close together, so the planets aren't that far apart, but they have pretty circular orbits. What else? The sizes of the planets, the radius of the planets, can be determined based on how much light the planet blocks out. If you know how far the planet is away from the star, and you know how much light it's blocking out from that star, you can calculate how big the object must be at that location to block out that much light. And so from each individual light curve, by seeing how much light is exactly blocked out from the planet at that distance, you can calculate how big the planet is itself. So we get the radius of planets using these transit methods. And of course, we get their periods, we get their distance from the star. And so kind of the main idea here is to combine the Kepler data with the radial velocity data. For those planets that we can use both methods on, we can use the radial velocity to give us the mass. We can use the transit method to give us the radius, and therefore we can get the volume of the planet. With the mass and the volume, we can get the density. And the density is really what's going to tell us, is this an Earth-like planet? Is it a water planet? Is it an ice planet? Is it gas giant planet? What type of planet are we looking at in these kind of special cases? Is particularly, right, do we want to know, is this a water planet, or is it a rocky planet, a terrestrial planet? Is it a Neptune planet? Is it a super Earth planet? Getting at the density will tell us these differences. Right. And so this is kind of what I was just saying. If we can combine the two methods together, these two different techniques for finding planets, that's when the science starts to get even more interesting, because we can get these things like density. The mass we get, the only way we can get the mass is from the radial velocity method, and the only way we can get the volume right now is from the transit method. And combining these two methods together is very, very lucky thing to do, but it can be done in a few small number of cases. And in those cases, we get the density. So that is kind of this kind of where the field is today, is just finding the densities of these planets. One thing that was noticed was that in some cases, when the planet transits around its star, the spectrum received kind of from the light signature of that star changes. And so people started to focus on how does the spectrum change, first of all, and what does it tell us about these planets? What would make the spectrum not be exactly the same? So what it turns out is that there's kind of this transition during a transit in cases of planets with atmospheres, where first the atmosphere gets illuminated by the light from the star, and then the planet starts to block out light. And then some portion throughout the transit, some portion of the star's light filters through the planet's atmosphere on its way to Earth, where it's detected. And so this light is getting altered by the planet itself. And so we can kind of focus on this light, and you can make a spectrum kind of subtracting the star's effect from this kind of effect on the star itself. It's kind of tricky, more tricky math stuff. Right, so here's kind of the idea here is that the planet itself is getting illuminated by the star, and how the light that hits the planet is transmitted to Earth could affect kind of our measurements of the star's transit. And so kind of some of those things are shown here, kind of the illumination of the atmosphere is kind of that lower blue color shown here. Kind of the secondary eclipse is that upper right portion as it's going behind, right? You can see the light getting reflected back in that case. So the light from the star is enhanced because it's bouncing off the planet and coming back to Earth. And if you're measuring these small amounts of light, that could cause an effect. So when I was mentioning earlier these atmospheres, and we'll talk about this more next time as well. There are certain signatures, right? If we can measure these atmospheres accurately, there are certain signatures that we expect to be directly correlated to life. There are certain things that if they are in your atmosphere, it's only possible through biological processes. And in particular, it is free oxygen. If there is oxygen available, kind of not being actively used in chemical processes, but just free oxygen in the atmosphere, like our atmosphere, which has about 20% oxygen, that is only possible through photosynthetic processes and biological processes. And so kind of looking for these kind of oxygen signatures, there hasn't been any detected yet. But looking for these oxygen signatures in the atmospheres of extrasolar planets is one of the newer techniques for searching for astrobiological indicators in other solar systems. But I haven't heard of any successful detections of oxygen yet. Any questions before I move on? All right. Here's just kind of more showing how the light passing through the atmosphere of the planet gets affected by the atmosphere on its way to Earth. And we can calculate all that math and do all of that. At certain wavelengths, the planet's atmosphere is more opaque. It blocks the light more. And this kind of tells us signatures in those atmospheres as well. What it blocks more effectively tells us more about that atmospheric evolution on this exoplanet as well. we can take the temperatures of planets using that secondary eclipse, seeing how bright that planet is as it passes back around the sun behind, and then kind of reappearing again. You can measure the amount of light that it kind of gives you the bump. And based on that, you can determine, especially if you can get it at multiple different wavelengths, you can get the temperature of the planet using some more fancy math as well. But the temperature, in some cases, you can then kind of extrapolate that to kind of like a global distribution. You might be able to determine, are these planets tidally locked? Are they gas planets, or are they terrestrial planets? And then making some of those assumptions, you can make kind of like daytime, nighttime, temperature profiles, and kind of things like that. And it has been done for about 40 planets. So they do have temperatures for some of these planets. But again, I'm kind of nervous. I wouldn't say these like are surface temperatures necessarily. These are kind of like reflecting temperatures. So kind of whatever the reflecting level would be. Right, so here might be like such a surface temperature map, kind of day side, night side. So the day side is warmer compared to the night side. The day side kind of being in the center here, the night side at the edges. Colder towards the poles, warmer towards the equator. This assumes, of course, no oceans, no atmosphere, no separate continents. It's just like one solid material, right? So you can imagine adding some of those complications in here. How would that change it? Here's another kind of model, same idea though. Kind of on the left, kind of the observations of the detection of the planet, and kind of on the right, what it kind of their model of the planet based on the detection. In this case, one of the problems is that they don't get any latitude information. They only get the longitude. And so they can't tell north-south variations. They can only tell east-west variations. And so based on the observations themselves, and then their model has to extrapolate the north-south. So kind of the pole equator difference, that is kind of based on their model, and then kind of the east-west difference is based on the observations. And then again, kind of going back one more time, the density. If you can get the mass and the volume of the planet, you can find the density of the planet. This tells you what the planet is made out of. So on this table, lots of things are plotted. We have kind of Earth mass on the bottom. We have Jupiter mass on the top. We have Earth radius on the left. We have Jupiter radius on the right. Kind of depending on how you want to measure those sorts of things. If you want to like kind of do Jupiter or Earth. Terrestrial planets kind of plot in a specific zone on this graph. Those planets are kind of outlined or kind of represented in green. The green planets are all the rock terrestrial planets that have been detected. The kind of solid curves here are for pure planets made of iron, pure planets made of rock, pure planets made out of water, up to those certain masses, after which it's not possible to have pure, well, it's not really possible to have pure planets of either any of those materials. You're going to have mixtures no matter what. But those would be the lines demonstrating pure planets. And so all of these green ones, these are all of our terrestrial planets or super Earths. These are the planets we would consider likely candidates for habitability. Kind of those would be the ones to focus on. We would then want to look, all right, we have these planets, where are they? Are they in the habitable zone as well of their host star? If they're the right type of planet, also in the right type of place, that makes them even a better candidate to continue kind of researching those specific targets. Anyways, continuing in blue, we have our sub-Neptunes, our Neptune-like planets, or our Uranus-like planets. These are our kind of water compound, ice compound, methane, ammonia, 15 Earth mass or so planets. And then in red are our Jupiter planets, or even like our super Jupiter planets. These are the hydrogen, helium, massive planets. But their densities, even though their mass is so high, their densities are actually still, in a lot of cases, very low. Because hydrogen and helium have the lowest mass of any element. So even though their mass is high, their density actually can be a huge difference. And then also their temperature matters, right? So hotter gases expand, they take up more space. So their volume is more, so that makes them less dense. If they're hotter, it makes them more dense. If they're colder, there's some of these factors to take into account as well. And then actually one more thing, just to go into that one more step. If they're colder, that means they're further away from their star. If they're hotter, they're closer into their star, right? So we can tell more and more things about these. Right, but the density, this is kind of the goal for every planet that we discover currently, get the density. If we can make the detection in both ways, that's kind of the best we can do with our current level of technology. So that's kind of the goal. Every planet we find, every planet we look for, can we get the density? That's what we want, because if the density is going to tell us, is it an Earth-like planet? Is it in the right place? If so, does it have a chance to be habitable? So density is what we want. Here we see a number of orbits for different extrasolar planets. Again, kind of just to bring back that point of the eccentricity. Right? Some of the orbits are very circular, some are very elliptical. Right? We plotted that, and it's the bigger planets that have the wider range in elliptical. Right? Some of the bigger planets had very high eccentricities and very low eccentricities, whereas the very small planets, almost none had high eccentricities. Nearly every planet that's been detected so far with present day techniques has been within Jupiter's orbit. There's a few that are beyond, but almost all of them are inside. And a lot of that is kind of just how long can we measure for, right? Because it takes, if it's outside of Jupiter's orbit, that means it takes as long as Jupiter does to make that orbit, right? So we have to measure then 2 to 3 times that length to detect that signal enough times to determine that there's a planet there, that it is a periodic signal, right? So if this is Jupiter, I think orbits off the top of my head at around every 5 years, every 5 Earth years. And that means to find a planet at a Jupiter's distance reliably, you need 10 to 15 years worth of data to make the same detection, because it only comes, that planet's effect is only measurable over that period of time, right? You need 5 years to measure it once, you need 5 years to measure it again, you need 5 years to measure it a third time, right? So it's 10 to 15 years to make this type of detection for something at a Jupiter distance. So that's just to say that kind of this is a technology and human experience limit, right? Measuring things beyond this distance, right? Their effects are smaller because the gravity is smaller. The effect of gravity is smaller at greater distances, but also just the amount of time for us to use is limited in our detections as well. I think I hit on all of these points with this last slide as well. Yeah, and so maybe just that last point, our solar system actually, based on kind of how much we found, the fact that we don't have, despite how many planets we have, the fact that there's not any with a high eccentricity might be surprising. And then just one planet to look at real quick. It's called the cometary hot Jupiter. It has an eccentricity of 0.93. So this is the highest eccentricity. It comes by its point. Its orbit is 111 days, but I think it only spends like 1 day super close to its planet, and then like the other 110 super far away. So this is a planet it's a Jupiter as well, right? So think about how much mass this is. I think this planet is very related to this one in the bottom right here. Or it would have a similar signal. It would be like combining the two on the right together, right? The huge wave but bent over. So when we look at the distributions of the planets that we have detected, something has kind of popped out. It seems that the Earth, super Earth, mini Neptune sized planet is extremely common, and the giant planets are actually much less common than expected. So the gas giant planets are found at a high rate because our techniques are better at finding those planets, but that how often they've been found is a lot lower than what would be anticipated by the same models that are finding the super high Earths and super Earths and mini Neptunes. So we're finding a lot of these smaller planets around stars much more often than the Jupiter class planets that we might expect. Let's see why those. There we go. And I kind of like I did make that caveat, right? Because most planets that have been detected have greater mass than Jupiter, right? So it's kind of weird that we expect more stars to have Earth and Saturn and Neptune like planets, but Jupiters are the ones that have been found the most. And most of those Jupiters have even more mass than our Jupiter does. But that's just based on the amount of stars that we're looking at and kind of the statistics that have been done. We expect to find fewer smaller planets because their effects are smaller. We expect to find more planets that are bigger because their effects are bigger. And we're just not finding as many of the bigger ones as we are the smaller ones that kind of are anticipated based on our instruments. We're finding more of the small ones than anticipated. We're finding less of the big ones than anticipated. But we are still finding more of the big ones. As kind of far as those orbits go, here is a graph kind of a planetary size or planetary radius versus orbital period. And kind of looking at these graphs, the idea is to start thinking of kind of ranges on some of these graphs where there are kind of Earth comparable planets. And so kind of the blue represents planets that would compare favorably with Earth, or the range on which planets would compare with Earth, whereas the brown is kind of the goal region of Kepler. And it found some that are kind of close. I don't think it found many that were directly Earth analogs. So kind of the surprising things that came out from looking at all of these different planets. The big one to me was kind of the highly elliptical orbits. So those orbits that are cometary planets. And then also hot Jupiters. So hot Jupiters have led to all sorts of problems in our standard solar system formation, and that how do you get a Jupiter close to the star? Does it form there, or does it travel there? And if it travels there, how does it get there? And then also, based on the findings, kind of there's just like a lot of planets out there that are not like any planets in our solar system. There's a lot of 1 to 15 Earth mass planets where we kind of top out at 1 and then we get to 15. We don't have any of that intermediate zone. Whereas there are a lot of representatives of that intermediate zone in the population that's been detected. And it turns out there's a lot of multi-planet systems. The best place to find new planets are around stars where you've already found planets. If you know it's got one planet, why not another planet, right? You know it was successful one time, why not again? Right, so the hot Jupiters, what's the deal? What's the deal with these hot Jupiters? So present day thought is that they cannot form close to the star. They have to travel there. The reason is that to form these hot Jupiters, well, to form a Jupiter, you need that icy material, and that icy material is not stable close to a hot star, right? You have to be in the outer solar system to collect the icy material and then collect the hydrogen and the helium. If you're close, the star is stealing all of that material, and it's too hot for the condensation of the icy stuff. And so you can't get big enough. So the Jupiter has to form in the outer solar system, or at least midway out in the solar system. So then what this means is for all the hot Jupiters that are out there, none of them formed where we see them today, which means they moved. So how did they move? Why did they move? What's going on there? We'll come back to that again. Multi-planet systems. Here are a wide number of planetary systems. Some people in class, I think, are doing posters on some of these. You'll notice that some of them show orbital resonances. We talked about that. So enhanced tidal effects there. We don't know about these kind of middle class planets. I think I'm missing a slide. I expected one more on hot Jupiters here. So one more thing about the hot Jupiters then. So they have to migrate. There are kind of two mechanisms for migration of the planets, right? Because they're in the outer atmosphere, outer solar system, and they're coming to the very, very, very inner solar system. So they have to travel a long distance. There are two methods. So first is kind of a gravitational drag from the solar nebula. Right? So the solar nebula is this big cloud of gas. As the Jupiter planet is forming, as it's collecting all of this gas, as it's traveling within that solar nebula, there's kind of this frictional effect that decreases the amount of energy in its orbit. And as it decreases the amount of energy in its orbit, it has less energy in that orbit, so it has to travel inwards to conserve angular momentum. So this kind of gravitational friction with the solar nebula, kind of as the Jupiter is forming, it pulls the Jupiter inwards. The second mechanism is something that we're already kind of familiar with. That would be due to tidal forces. So once the Jupiter planet gets kind of a critical distance from its star, the tidal effects can become important enough to continuously draw that planet closer and closer and closer, especially if that Jupiter planet gets on an eccentric orbit, right? If it comes close to the star, that enhances that gravitational effect. So if it's on this eccentric orbit, tides are very, very, very strong at certain periods. If you get orbital resonances with other planets that are there, that could drive those tidal effects again as well. Right, so these tidal effects combined with this solar nebula friction drives these Jupiter planets as they're forming from the outer solar system into the inner solar system. At least that's the hypothesis to explain the movement of Jupiter planets to become hot Jupiters. All right. And then, yeah, there's a lot of multi-planet systems out there, like I mentioned, especially when radial velocities were first being looked at and transits weren't available yet. The best candidates to find extra planets was around known stars that already had known planets. So the radial velocity the method definitely tried to like focus where it had already been successful. Let's see. It turns out there's a lot of low mass planets. So based on those density calculations, that bulk density, there's a lot of low mass planets that are not rock and iron. We think there are some that there might be a carbon planet. There might be a water planet. There might be low mass hydrogen helium planets with strong magnetic fields. There's some things out there that we don't have representatives of our solar system. So getting out to explore those might be very interesting. Here's just kind of more graphs showing density. All right, so formation of other solar systems. How do we need to modify our theory of solar system formation? Are planetary systems like ours common? I kind of discussed those modifications just a minute ago, right? So here is kind of that picture I thought was a couple slides earlier of the solar nebula friction. This is what I'm talking about. Here's the picture of the solar system nebula friction drawing the Jupiter planet inwards. Right, the hot nebulas, hot Jupiters made us change. That was a big deal. Yep, here's all the slides. I was slightly out of order. I got ahead of myself. Yeah, so the planetary migration due to those kind of friction with the nebula, you get the waves as well forming because it's on periodic time scales. Gravitational encounters and resonances, we mentioned that. Elliptical orbits. Yep. One thing we have to watch out for that I worry about is that our methods of detection are biased towards bigger planets. And so we have to be careful about the statistics that we use for our planetary populations, and that we are detecting more bigger planets, but it's harder to form bigger planets. It's just that our methods of detection are biased towards finding those bigger ones. All right, and then what about other planetary systems? How do they compare towards ours? Well, we did find lots of multi-planet systems. We do know of terrestrial planets in habitable zones today. There are Many of you are going to present posters on terrestrial planets in habitable zones next week. And so it seems like our system is not rare. It seems like as many as 20% of stars could have rocky planets, terrestrial planets in, and not only just terrestrial planets, but terrestrial planets in habitable zones. Right? So if 20%, that's a lot of stars, that's a lot of planets. That's a lot of planets in habitable zones. That's a lot of chances for life. Next time we'll talk about life. We'll only talk about astrobiology. And then kind of just where's the future of this? So this is kind of the cutting edge of astronomy right now, or at least kind of the intersection between astronomy and geology, these extrasolar planets, finding more and more of them. Astronomy is working on a couple other things too, gravitational waves being a really cool thing. So this is kind of still new, right? This has only been happening, finding these extrasolar planets has only occurred since the 1990s, really. And it's exploded with Kepler starting back in like 2009. There's a new spacecraft working on this same sort of method as Kepler that launched just recently as well. Let's see, and I think that's Gaia. So Gaia is one. Gaia I don't think is launched yet, but it's trying to use that method of interferometry to measure the positions of stars very, very accurately. So this one's the one to attempt that astrometry method that has not been successful so far. But until Kepler, transit hadn't been successful either. So just because something has not been successful so far does not mean it never will be. TESS launched, I think, last year. Cheops is another one. These are both transit method spacecraft. I expect TESS data to be coming shortly. Direct detection with the James Webb Space Telescope coming, I think, in 2 or 3 years. That's going to be more and more likely. This is like Hubble times 10. So with like the high level techniques there, I believe we'll get more direct detections of planets. All right, and that's all I have for today. Any questions? All right.